In this video, we are going to take a look at factors that affect the reaction rate. Please read the OER textbook chapter section 12.2 for more details. The first factor that we are going to take a look at is the effect of physical state of the reactant. So in this case, we are going to take a look at in terms of the surface area of the reactant. Okay, so what do we mean by that? Okay, so let's take a look at example. Okay, so the example that I'm going to use is the solid iron that react with hydrochloric acid. Okay, so this one is going to react and is going to form iron chloride and hydrogen gas. So that means in this case, when these two react, you are going to observe the formation of the hydrogen gas. Okay, so the hydrogen gas is going to bubble out. This picture shows the two forms of iron. Okay, so one is in the powder form and the other is in the nail form. Okay, so these two forms has different surface area of interaction. Okay, so the powder form is going to react more rapidly with hydrochloric acid and produce more bubble of hydrogen. On the other hand, the iron nail is going to react more slowly. The reason for that is because the surface area exposed to the acid is much less than of the iron powder. Okay, so as you see here, there's less hydrogen gas bubble is being formed. Okay, so this just makes sense because if you think about food that you eat, right? So if you chew your food very well, your body is going to digest that faster than if you swallow like a big chunk of hamburger or something, right? So your body is going to be able to digest that slower, right? So in this case, we can conclude that increasing the surface area for the interaction is going to allow for more rapid reaction rate. Okay. So the second factor that we are going to take a look at is the concentration of the reactant. Okay, so the lecture demo for this is going to help you to understand this. The reaction that we are going to take a look at today is going to be between the sodium thiosulfate and hydrochloric acid. Okay, so when these two react, it's going to produce sulfur solid. Okay, so sulfur dioxide, water, and sodium chloride. But the species that we are going to actually observe is going to be the solid sulfur. Solid sulfur, when it's produced, is going to give you like a light yellow color. So that's what we are going to see. So what I'm going to do is that I'm going to add sodium thiosulfate into the test tube and draw red marks on the test tube. Okay. And then I'm going to start a timer when I add hydrochloric acid into this test tube. Okay. So that means once it reacts, it's going to form solid sulfur. Okay, so solid sulfur would have yellow color. So because solid, right? So once it's produced, it's going to obscure the red mark that is on the test tube. So that means I will no longer see the red mark once solid sulfur form enough. Okay, so that's when I'm going to stop the timer. Okay. So what I'm going to do is that I'm going to compare two different concentrations, right? Because right now we are looking at the effect of concentration. So I'm going to look at the concentration of sodium thiosulfate. Okay, so one is 2 molar, the other one is 1 molar. Okay, so we are going to take a look at which one would react faster. So what I'm going to do is that I'm going to do this twice, right? So one with the 2 molar concentration of sodium thiosulfate and the other one with 1 molar of sodium thiosulfate. And I'm going to compare the time that it takes for us to no longer see the red mark on the test tube. Okay, so right, to see which one is happen faster. So here are the two test tubes of sodium thiosulfate. Okay, so these two have different concentration. This one have 2 molar concentration, and this one is 1 molar concentration of sodium thiosulfate. Okay, so these two test tubes, I actually make the red mark. Okay, for these two test tubes. So if you see that, you are going to see it's going to be a heart shape right there. So, and another one that we have is going to be the same concentration of hydrochloric acid, okay, with the same amount as well. Okay, so what I'm going to do is that I'm going to add hydrochloric acid into sodium thiosulfate. Okay, so once these two react, it's going to form sulfur, the solid sulfur, which is has the yellow color. It's going to obscure us from seeing the red mark of this test tube. Okay, so we are going to time. I'm going to use stopwatch. Okay, so we can time. So I would like you to use your own stopwatch as well to help me here. So we are going to time this together and see, we are going to stop the time when you are no longer see this red mark. Okay, so that's when we're going to stop our time. Okay, so let's take a look at this together. Let me actually move this away. So this one is the 2 molar concentration. So I'm going to add hydrochloric acid to it and then start a timer. Okay, so 1, 2, 3, and I'm going to start the timer. All right. It took about 8 seconds. Okay, so now I no longer see that red mark anymore. Okay, so as you see, right, the light yellow color, that is the solid sulfur that is being formed. Here is the 1 molar concentration. Okay, so I'm going to again add hydrochloric acid and then start the timer. So this one take a little bit longer. Still see the red mark. I still see it. Oh, right there. So it take about 32 seconds. Okay, so for you no longer to see the red mark. Okay, so here I want you to compare. This is the reaction that with the 2 molar concentration of sodium thiosulfate. Okay, so this is the reaction with the 1 molar concentration of sodium thiosulfate. From the lecture demo that you see, right? So we observe that the 2 molar sodium thiosulfate react with hydrochloric acid faster than the 1 molar concentration. Okay, so in this case, we can conclude that as the concentration of the reactant increase, you are going to observe that the rate of the reaction also increase as well. Okay, so it go faster. Okay, all right. So the third factor that we are going to take a look at is temperature. Okay, so this lecture demo is going to involve with alkyl-sulfur reaction, which involve with the sodium bicarbonate. Okay, so this part right here come from sodium bicarbonate that is going to react with citric acid. So this part right here is coming from citric acid. When these two react, it's going to produce water and carbon dioxide. So I'm going to run this reaction under 2 temperature. Okay, so one is in hot water and the other one is in cold water. Okay, so and I am going to trap this formation of carbon dioxide by using the balloon. Okay, so I'm going to trap that. So that means I'm going to put the balloon over this. Okay. So what I want you to predict is that I would like you to predict the relative size of the balloon. Okay, so over flask 1 and 2, which one is going to become bigger, faster? Okay, so that's what I want you to predict. Okay, so let's take a look at the lecture demo. Here are the 2 flasks that contain different temperature of water. So this one contain cold water and this one contain hot water. So above this flask are balloons that contains crushed 2 tablets of alkyl-sulfur. So what we are going to do is that I'm going to add the crushed alkyl-sulfur into water so that way the sodium bicarbonate and the citric acid can react and form carbon dioxide. And we are going to trap carbon dioxide gas with the balloon. Okay, so and you can compare the rate of the reaction by looking at the relative size of these 2 balloons, right? So the one that is getting bigger is going to indicate that the rate of that reaction is faster. So let's take a look at both of them. Okay, so I'm going to add the alkyl-sulfur for the cold water real quick. Okay, so and the next one I'm going to add to hot water. All right. As you can see, right, the hot water, the balloon is actually getting bigger right away, right? So that means the rate of the reaction for the temperature, the hot temperature is actually faster than in the cold temperature. From the lecture demo, we observed that the balloon size over the higher temperature is actually getting bigger faster than over the colder temperature, right? So in this case, our observation would be the reaction in hot water go faster than the reaction in colder water. The reason for that is because you observe that the balloon is actually getting bigger in a shorter time for the hot water. Okay, so that means in this case, we can conclude that as the temperature increase, okay, so the reaction rate is also going to increase as well. This makes sense, right? If you have food and you forgot to put into the refrigerator, right? You leave it outside at room temperature, it's going to spoil faster than if you put it in the refrigerator at colder temperature, right? The last factor that we are going to take a look at is the effect of the catalyst on the reaction rate. Okay, so in this case, I'm going to show you the lecture demo of the composition of hydrogen peroxide. Okay, so once hydrogen peroxide decompose, it's going to give off water and oxygen. Okay, so oxygen is going to be the one that we are going to observe in this lecture demo. Okay, so let's take a look at it real quick. This test tube contains 10% of hydrogen peroxide that has been sit outside at room temperature for about an hour now. Okay, so I will let you look closer. As you see, if you look closer, you will see that there is no bubble form at all, right? So it's barely, there might be one in there. So in this case, it tells us that the decomposition rate of the hydrogen peroxide at room temperature is very slow. Okay, so that means it's not going to happen like right away, right? So you probably have to let this sit for a day or something in order for you to see the oxygen gas that is being formed in this solution. Okay, so now I'm going to accelerate this reaction by adding the catalyst. Okay, so the catalyst that we are going to use is the potassium iodide. Okay, so I'm going to add potassium iodide into our 10% of hydrogen peroxide. So in this graduate cylinder is the hydrogen peroxide that you just seen previously. Okay, so I'm going to add the catalyst into this to accelerate the decomposition of hydrogen peroxide. Okay, so I'm going to add to this. Okay, so if the reaction occurs, you are going to observe the bubble of oxygen gas. Oh, yep, if you look closely, so that bubble right there is the bubble of oxygen gas that is being formed. So I also add some soap into this solution as well, so that way you see the bubble clearer. Okay, so in this case, you see that bubble that is being formed is so that's bubble right there. That's the oxygen gas that is being formed. Okay, so the color is a little bit yellow. It's coming from the iodide catalyst that is producing the color. Okay, so right there. So you can see that the catalyst does accelerate the decomposition of hydrogen peroxide. As you see from the lecture demo, right, the uncatalyzed reaction of the decomposition of hydrogen peroxide is happen very, very slow, right? So it's barely generate oxygen gas. However, if you're looking at catalyzed reaction, you can see that a lot of oxygen gas is being formed, right? So it's causing the reaction to go faster. In this case, potassium iodide is the catalyst. Okay, so it's causing oxygen to form faster. So how do I know that potassium iodide is the catalyst, is not the reactant? Well, if you're looking at the uncatalyzed reaction, you still see that in the absence of potassium iodide, the reactions still occur, right? But at a slower rate. So that means potassium iodide is not the reactant. So only the hydrogen peroxide is the reactant. So the conclusion of this is that in the presence of catalyst, the reaction will go faster. Okay, so I want to point out one more term. Okay, so whenever you see the term of inhibitor will behave the opposite of the catalyst. Okay, so the inhibitor would be the one that is going to reduce or slow down the speed of the reaction. Here is the summary of this lecture. Okay, so we're looking at different type of factors that affect the reaction rate. We're looking at the surface area, physical state of reactant, right? We're looking at the concentration, temperature, and also last one is the catalyst.